Design model. In this lecture, the detail of the design model will be covered. So, the following are the components of the design model. The first is the data design. It is the low level design. Data design is considered as the low level design. Data design deals with the behavior of data, such as storage of data, retrieval of data, and all the associated operations on the data, such as how to insert the data, what type of data will be inserted, data retrieval, data updation, data deletion, data selection, and how data will be stored in the tables. So how many tables are required to store the data? Is the table normalized or further need more normalized data? So data design is very much important. So before designing the tables for the data, we construct the entity relationship diagram and then associate these entities together, and then convert the entities into schema, and then put constraints on the data. So putting constraints on the columns of the table limits the behavior of the data. So data design is very much important. Above the data design comes the low level software design, which is the construction of concrete details. Mostly the backend programming is involved in low-level software design. The data insertion, manipulation, controlling is responsibility of the low-level design. And then architecture design. Architecture design shows the relationship of the major components or modules of the software. Architecture design show the structure, the plan of the modules, components, and their association together. And then on the top of architecture design is the interface design, which shows software system interfaces of how user will interact with the software. So user needs attractive interfaces, easy interfaces through which users can interact with the different components. And then procedural design. It defines the procedural activities. Procedural activities shows what type of actions are needed, what type of actions can be expected from the software. So based on these procedures, we laterally design the architecture and low level design. This is the design model. So first come the procedural design. So what comes in the procedural design? Process specification. Process specification means how the process will be executed, what type of activities are required to execute the software, and we also need a control specification and state transitions. For example, state transition shows the different states, possible states. If we take example of the door, there are two states. Door can be either closed or open. So different states are specified in the procedural design. And then interface design. Why we need interface design? Because the data is passed from the user to the system and laterally stored in the database through interface design. So data flow diagram actually need the interfaces. And then comes the architecture diagram. So when data is passed from interface, so the architecture design is then responsible for communicating for passing this data among different components, and then the data design, which is actually the data dictionary. So this is the hierarchical representation of the software design. First comes the procedural design, interface design, architecture, and then data design. And in between architecture design and data design is the low level software design or control language, which is actually the backend programming language, which is responsible for controlling the activities between the data design and the architecture, high level architecture design. Now, what is abstraction? Abstraction makes us to concentrate on a problem at some level of abstraction without going into the low level or concrete detail of program or system. This means while making the architecture of the software and specifying the structure and plan strategy of the software, we adopt abstraction property. Without going into concrete detail, we specify the high level creation of the components. While refinement is the opposite process of the abstraction, which is the process of elaboration of going in concrete detail for low level solutions. So in refinement, what we do, we put the problem and then go into the detail for getting the solution. So here decomposition of program or module takes place. So decomposition is the property used or adopted for refinement. Abstraction and refinement are complementary concepts. So both the concepts are used laterally when we proceed in this course. So you will know why refinement and abstraction both are necessary. Modularity. The name shows modularity. The modularity name show that we make more and more modules. In this concept, software is composed into many components or called modules, such that each module exhibit different property from other module, and all the associated components of the particular module will work from one main goal. It follows the divide and conquer concept. A complex problem is broken down into several manageable pieces. Let us take P1 and P2 be the two problems. Let E1 and E2 be the effort required to solve them. So if C of P1 is greater than C of P2, means if the complexity of the problem 1 is greater than complexity of the problem 2, then effort required to solve the problem 1 will be greater than effort required to solve the problem 2. Now, complexity of the problem that combines the two problems is greater than complexity each problem is considered. Let's see this. Here you can see that when we combine the both modules and take the complexity of the combined modules together, and on the other side if we take the individual complexities of individual module, so the complexity of the whole combined one module will be greater than individual, and this means the effort required to solve the complexity of the whole one module will be greater. So this means if we decomposed a module into several manageable modules or a system into several modules, then the complexity decreases, and thus the effort required to solve or implement the module will also decrease. But remember that this is achieved up to certain extent. If we start decomposing and make several up to 100 modules, so this does not mean that effort will be reduced to a minimum. There is a certain region of minimum cost. Why? because there can be many reasons. If we decompose the module into the or system into two modules such that there is association between these two modules, so this means creating that association, which is also known as coupling, is not easy. And when a decomposition process progress and we decompose the system into 2, 4, 8, 10 and so on, and many modules to many modules, then the number of coupling increases, and this is not a good. So decomposition is a good approach and it reduces the effort required to implement the software, but the disadvantage is that the number of coupling also increases. So if the number of coupling increases, so that become difficult for programmers to integrate, and then when laterally when we want to reuse some of the components or module in some other systems, so that is not easy, and then we have to split that relation or coupling, and then have to integrate in other modules, so that become difficult process. Or the second approach is that for integrating two modules we might need some more components, so that is also costly. So there is a decomposition is good, but up certain level, so that region is called region of minimum cost. Now come to the control hierarchy. These are the few definitions. This is the control hierarchy. We have here one module, and then these are the further modules. So these are the modules. There are two concepts used here. One is called the width and is called the depth. So width is the span of control and depth is the number of levels of control. Means when the number of modules increases in breadthwise position, in breadthwise fashion, this means the width increases, while the depth is the height of the modules in a hierarchy. For example, the depth here is 1 2 3 4 1 2 3 4, so the depth is 4, and when the number of module increases, there is both chances of either increasing the depth and the width. So one other two concepts used here are fan out and fan in. So what is fan out? The number of modules that are directly controlled by another module. So the fan out, for if we take this, so the fan out of this M module is 3, because it is controlling the 3 module, and fan in is that how many other module are controlling the particular module. So if we take this R module, so the fan in will be 4, because 4 module are controlling this module. Remember, one thing is that decomposition does not mean that we split one module into 2. This is not necessary. Yes, we can it, but this also become the sub module of the one particular module. Decomposition here means that rather than considering one system as a whole, one module, we take it and consider this system in many modules and then integrate it. So this does not mean that M is subdivided into A, B, C. If we divide it, decompose it, this means M is now no more here, but M is here and A, B, C are also here, but M is controlling the A, B, C. So decomposition does not mean that we split the one module into 2 parts such that the main module become no more. No, this is not correct. In decomposition, the main module exists, but rather we distribute the system in the different module. So this was all about